Very fine morning, everybody. This is ASM Raju, and in the today's lecture related to operational research subject, I would like to deal with the topic simplex algorithm in operational research. As far as we have been considered the linear programming technology or linear programming techniques, it is a part of the linear programming technique that the normal mathematical methodology is one subtopic of linear programming. Second one, it is an algorithm basis, that is computational algorithm basis in linear programming for solving the complex state of problems at a different application point of view. Coming to the third one, that is a big M methodology and general method. That is a fourth. Moving on to the linear programming technology, simplex algorithm is also plays a major role for solving the complex situational problems in a very much easy format by following the stagnants or algorithms as a flow chart and getting obtained the optimum or feasible solutions. Feasible solutions. We'll be having a look in depth. As far as our syllabus has been considered, we'll be having a minute glance over the unit 1 of the syllabus. Till now, we have been performed with respect to the development, the definition. These are the basic introductory parts and the theoretical part of the unit 1 related to the operational research. Coming to these allegations, that is linear programming problems and formulation, how this linear programming is subclassified, and for this, how the mathematical relations and the solution of a complex kind of problems we have been learned in the previous classes. With respect to the graphical solutions, we have been seen in the previous class, and big M method we have been seen in the yesterday's class. And in the today's class, we'll be dealing with a simplex method, the subtopics that are being existing in the linear programming problem formulations. Yes, what is meant by a simplex algorithm technique or methodology used in a linear programming for solving a typical kind of problems. Indeed, to get the feasible solutions. The unique optimal solution to the linear programming would be occurring at corner of the feasible region. As this point clearly specifies that in the graphical representation method, when you have been plotted the graph with respect to the given polynomial equations by getting the constraints or by substituting the variables, will be obtaining the constraints, and if one constraint has been obtained, that simultaneously if we've been submitted that constraint in an equation, will be getting the major constraint value, and we'll be plotting with respect to an results obtained as per the x coefficient and y coefficient. And upon plotting, we can conclude that whether the region which is specifying with respect to the values obtained after the solvation is within the feasible corner or not. It specifies a basic phenomenon for validation of the feasible region. Alright. In fact, it's true that for any linear programming, the optimal solution occurs at the vertex of the feasible region. Because the fact is key to the simplex algorithm for solving the linear programming problems. So vertex, there is x and y values will be getting obtained in the feasible region relates to the solvation of the complex problems by utilizing this simplex algorithm for solving those kinds of problems. Simplex algorithms will be starting at one vertex of the feasible region at each iteration. So here iteration specifies that for each and every equation based on the constrained values, that is x1 y1, x2 y2, x3 y3. So for each and every constrained values will be having one vertex points, and simultaneously if the number of constraints has been increased, the vertex points will be increased. And by substituting of those values graphically, we will be obtaining a feasible region or infeasible region can be specified as per the basic equation. And that iterations will be starting for feasible, and it moves to another vertex, from one vertex to another vertex, which improves the objective function as it does until it reaches the vertex corresponding to the optimal linear programming solution. So up to upon different number of iterations, it will be getting moved on, or it will be continuously accessing different kinds of values upon iterative methodology of solving until it reaches the corresponding optimal linear programming solution. So it is a method, iterative kind of method utilized for solving the typical kind of problems by this application in the case of linear programming problems. Basically, it has been developed by Dancing in the late 1940s. Since then, number of different versions of this algorithm has been developed, and these are named as revised simplex algorithm. The basic steps that are involving in this simplex algorithm method we'll be looking here. The step one relates to convert the given problem to a linear program in a standard form. So obtaining of an equation. So generating the equations and identifying the different constraints given at each and every level of the equation. So the level of the strategy of the problem, identifying the LHS terminologies and equating them to the RHS terminologies, and applying these linear programming formats that the RHS should be greater than or equal to 0 of the LHS. Right? If at all, and the second condition of linear programming it is that it should be non-negative. If at all it is negative, we will be multiplying with the minus k. And later on, we used to add in the step 2 of these linear programming conversions, we'll be adding the lead variables. Later on, artificial variable will be getting added. If the minimal range of the problem or equation has been obtained, then we will be multiplying with a large positive number with positive number, positive sign implication. If at all it has been minimal in range of linear programming, then we'll be multiplying with that large positive number with opposite sign, that is negative m to the obtained value, making us convenient to do the RHS as a positive sign, that is equating to non-negativity. That is the step one involving in the simplex algorithm method, that is converting the linear programming to standard form. So conversion of the entire problem to standard form implies these conditions, in which that we have been utilized the conditions for solving the linear programming in the general mathematical calculations by applying these four different steps. The second point here specifies that obtain the basic feasible solution, BFS, basic feasible solution, from the standard form. So the constraints will be obtained. One constraint will be equated to the RHS, and upon getting the constraint will be getting added to the basic constraint. When it has been equated, will be obtaining the second constraint also as well, and plotting those with the obtained vertex points of x1 y1, x2 y2, x3 y3. We will be identifying those values graphically and identifying the region that is existing is within the feasible range or not. That is a feasible solution, BFS, basic feasible solution, from the standard form. So the conversion of linear programming to standard form specifies the equation generations for solving the point basic given constraints. By the obtained values, we will be plotting a graph by utilizing the graphical representation method and identifying the basic feasible solution from the standard form. Later on, determining whether the current basic feasible solution is an optimal solution or not is a very nearest way of obtaining the solution to the standard solutions existing or not. If it is optimal, then we will be stopping. If the current basic feasible solution is not optimal, which non-basic variable should become a basic variable, and which basic variable should become a non-basic variable to find a new basic feasible solution with a better objective function value. So if the obtained value determines which non-basic variable should become a basic variable, if the current basic feasible solution is not optimal, then you have to determine the non-basic variable should be a basic variable, and vice versa, basic as a non-basic. And then we will be obtaining a new basic feasible solution with a better objective function. We will be identifying a basic objective function and repeating the step 3, that is solvation of the opposite sign variationals containing the equation, that is basic to non-basic, and those non-basic equation will be taken and applying the standard linear programming concepts to the equation, the obtained equation, for solving in a better way, that the application of these variables, standard variables, next additional variables and large positive numbers, this will be getting added and simplification will be done. and identifying the values, and those values should be plotted in the graph, and have to identify that they are existing within the basic feasible solution formats. Until and unless we have got the basic feasible solution as an optimal range, the step 3 need to be carried on in a cyclic process, or that we will be calling that iterative process. Number of times the repetition of similar process indeed to get the optimal solution or basic feasible solution to an optimal range, then we will be stopping the entire process. And this is the methodology that is being going on in the simplex algorithm process. And here the algorithm specifies that yes or no commands. Here there is a basic phenomena. If VFS basic feasible solution is optimal, okay, then we will be stopping the algorithm, or else continuously it will be verifying with respect to the standard basic feasible solution to an optimal solution verification. And if it all not satisfies those conditions, we will be repeating in a cyclic process that we will be calling as an iterative methodology, as we have specified. And the objective functional values will be getting taken, and those will be getting converted to a basic to non-basic, and those non-basic solutions will be getting forwarded to until you get the optimal solution. And if at all the optimal solution has been obtained, simultaneously it will be getting stopped in work. Let's move on with the related concepts behind it. The related concepts behind it. Standard form. Standard form specifies that almost all the constraints or equations and all the variables are non-negative. We are having the furthermore or basic feasible solution in the sense where all the variables are non-negative. That's the basic condition that is existing in the linear programming formulation process. So the next one is non-basic variable. A chosen set of variables where the variable is equal to 0. So it should not should be equal to 0, or must, or should be greater than, maybe greater than 0, the variables, but non-negativity. Beyond the 0, the variables will not be getting existed. So what are the basic variables here? The variables remaining which satisfy the system equations at a standard form. When the standard equations has been identified with respect to the given constraints, then those variables are called as an basic variables. Let us move on with an example. Manufacturing of furnitures. Let the company name be Dakota. Dakota Furniture. It makes desks, tables, and chairs. Each product needs the limited resources of number, carpentry, and finishing, as described in the tabular column that has been specified in the tabular column below. At most, 5 tables can be sold per week. Maximize the weekly revenue. So here it is clearly specifying that as per the given data, by consuming the given data, as an average per week, 5 tables will be getting sold, and maximize the weekly revenue. Here, the constraints need to be taken as a priority. So, what are the constraints existing? Lumber, there is board in feet. So, 5 tables need to be sold. 5 tables has a demand per week that will be sold, and how the manufacturing can be availed for satisfying the demand of those products, that is tables per week. So lumber, board feet 8, for desk 8 feet, table 6 feet, chair 1 feet, maximum availability is almost the available lumber wood in the feet it is 48. So hence upon combination of desk, table, chair need to be manufactured among that 48 maximum available. Next, what are the working hours need to be done for finishing hours? 4 hours for desk, 2 hours for the table, 1.5 hours for the chair, and maximum available time it is 20. That is below the total number of hours that has been considered for manufacturing of this desk, table, chair is below the maximum available time hours. That is 4 plus 2 6 plus 1.5, that is 7.5, and 7.5 is less than 20. Moving on to the carpentry hours, 2 hours for the desk, 1.5 hours for the table, 0.5 hours for the chair, and maximum available time it is 8 hours. And what is the maximum demand that is existing? That is, for the desk there is no any limit, and hence for the table we have been specified that per week only 5 tables can be sold, and hence specifying that constraint, that is 5, and for the chair it is unlimited. Moving on to the price, for the desk it is per unit 60, considering in dollars. For the table it is 30, and for chair it is 20. So considering these values, we have the constraint that has been obtained for only the tables. That is maximum 5 tables will be sold. So RHS, maximum demand RHS is equal to 5. So finishing hours need to be specified. There is lumber board 6 feet. Finishing hours 2, carpentry work 1.5 hours need to be done by the workers. Carpenter finishing need to be done by the fitting alignment or assembly conditions need to be satisfied with respect to the raw material, and have to satisfy those demand. That is, and it has to be sold out for $30. So we'll be having a look of the major constraint equation, that is price constraint initially. Let x1, x2, x3 be the number of desks, tables, and chairs that have been produced. And considering Z is a weekly profit, then constituting Z is equal to 60 x1, 60 desks plus 30 into 30 tables, 30 x2 plus 20 x3, that is chairs. And moving on to the lumber boards, that is maximum feed that is being available, 8x1 plus 6x2 as per the table of column plus x3, 1x3 less than or equal to maximum available 48. So 48 is almost greater. Next one, 4x1, that is finishing hours finishing, 4x1 plus 2x2 plus 1.5x3 less than or equal to 20. So that is the equation taken. And the third constraint equation, it is carpentry, 2x1 plus 1.5x2 plus 0.5x3 less than or equal to 8. So here for x1 there is no any limitation. For x2 there is no any demand limitation. Sorry, for x3 there is no any demand limitations. So for x1 and x3, that is for desk and chair, there is no any limit of limit for the demand. For only the table we are having the demand that is also for 5, and constituting x2 is less than or equal to 5. and considering x1, x2, x3 is definitely greater than or equal to 0. And solution with an considering the solution with an simplex algorithm by imparting or by implementing the sequence of steps. So let us recall once again the steps. That is standard form, basic solution. There should be non-negative. So hence we are getting the almost all the values are non-negative. Almost all the are positive only. So non-negativity is clearly specifying here in the equations, and it is feasible. And we can consider that BFS is non-negative. And setting choosing a set of variables already x1, x2, x3 has been chosen and equating to 0, and formulating or satisfying the system conditions and moving on to a possible solution breakup. So first introducing the slag variables and converting the linear programming to a standard form and writing in a canonical form or chronological form. So row 1 taking z, that is minus 60 into 1 when it has been moved into the left hand side, that is z, z minus 60x1 minus 30x2 minus 20x3 equating to 0. Simultaneously the row 1 8x1 plus 6x2 plus x3 plus s1 standard variable 1 slag variable 1 is equal to 48. Step 2 row 2 4x1 plus 2x2 plus 1.5x3 plus this slag variable is equal to 20. Next row 3 2x1 plus 1.5x2 plus 0.5x3 plus slag variable 3 is equal to 8, and we are having the constraint that the weekly producing tables is 5 in demand. So row 4 x2 plus slag variable 4 is equal to 5, and we are definitely assured that the slag variables that has been considered and the variables that has been considered is definitely greater than or equal to 0 because they are non-negative in cadre. So obtaining a starting basic feasible solution, considering x1, x2, x3 is equal to 0, feasible solution for original problem. When we have been equating these three variables to 0 and the four other variables, that is nothing but the slag variables we have been taken and determining by the four equalities in the obvious basic feasible solutions. Considering x1 equal to x2 is equal to x3 is equal to 0, and s1 is equal to 48, s2 20, s3 8 RHS terminologies, s4 that is 5, and determining whether the current basic feasible solution is optimal or not, that is the third step need to be identified. uh, we are right with that anyway. Z value is increased by increasing some non-basic variables. If non-basic variables has non-negative coefficient in the objective function row, current BFS value is optimal. However, non-basic variables have negative coefficients because the RHS terminologies has been brought into the LHS terminology. Definitely, they will be having the negative coefficients, and hence it is not an optimal solution. And then we have to proceed for the new basic feasible equation. So what we have to do at this terminology, the z increases most rapidly when x1 is made non-zero, and entering that x1 is the entering variable, and then examining the row 1, x1 can be increased on to 6 and more than the 6 makes this slag 1 will be less than 0. Similarly, row 2, row 3 and row 4, by giving the limitations of 5 comma 4, Here we have been considering that S2 is given simultaneously equating with respect to the 5, and S1 is equal to, then we have been taken with respect to the X1 increased by 6, X2 5, X3 it is 4, like that. But there is no any limitation for X1, and we all clear that the smallest ratio is the largest variable of entering the variable if the current basic variable is non-negative. Say obtaining variable is non-negative. Thus by row 3, x1 can only increase to 4 and becomes s3 is equal to 0. And we say then we will be saying that s3 is leading variable and row 3 is an pivot equation. Hence, considering the row 3 equation, that is row 1, row 2, row 3 equation, 8, almost having the 8 minus, that is, we are having the feasible demand for it is and 5, that is equal to 3, and hence that is obtaining with respect to non-zero value, and we say S3 is an leading variable. And by considering this row 3 equation, for that situation we are considering the row 3 equation is a pivot equation, that is nothing but existing feasible equation can generate the solution for it. And we must rewrite that situations so that the values of basic variables can be read out, and simultaneously solving the equation which has been obtained as an BFS, that is basic feasible solution. And uh, considering the simplification factors of the equation, that is rho naught or rho 0 plus 60 R3, nothing but calculating with respect to the R3 equation that has been taken. Hence, z plus 15x2 minus 5x3 plus 30s3 equal to 240 after performing the rho naught plus 60 R3. So 60 has been multiplied with respect to the R3 equation, and next upon adding this rho 0 with respect to the 60 R3 obtained equation, it will be generating that R4 is equal to R4. There is an equating factor, there is a justification process, and simultaneously upon substituting those, we will be obtaining this z value as an 240, slag variable 116, slag variable 24, and considering this basic phenomenal equation x1 is equal to 4 and r rho 4, that is an, yeah, slag variable 4 is equal to 5. So the new basic feasible equation is x2 is equal to x3 is equal to, next slag variable 3 is equal to 0, but x1 is equal to 4, slag variable 1 is equal to 16, slag variable 2 is equal to 4, slag variable 4 is equal to 5, and making maximum that obtaining these all equations upon substituting into the basic equation, equating the z value or substituting that values, overall these values in the row 0, will be getting that z is equal to 240, right? And checking these optimality with the current that is already generated a basic feasible solution, and repeating the steps until the optimal solution is reached. And how, in what way we will be seeing here. We'll be increasing the z value fastest by making x3 non-zero. There is nothing but x3 will be enters, and how it will be verified. X3 can be verified to at most of x3 is equal to 8. Then s2 is equal to 0. S2 will be getting left. Sorry, x3 will be equated with respect to the 8, while s2 is equal to 0 because it leaves. And considering that equation with respect to row 2, rearranging that equation, the pivot equation, it gives the this result, that is about row 2 or not. We'll be verifying it upon equating. Minus 2x2 plus x3 plus 2s2 minus 4s3 is equal to 8. That is row 2 is multiplied with respect to the 2. So when the variables has been brought towards the LHS side from the RHS side, containing the value of negativity, and the equations has been moved from RHS to LHS. Now the row operations with R2 eliminates x3 to give the new system. R0 is equal to R0 plus 5 R2, and hence R1 is equal to R1 plus R2. Performing these equations, R3 is equal to R3 minus 5 R2, R4 is equal to R4. And upon performing these iterative methodologies for the rows that we are being existing, that are being existing for us, the basic feasible solution is now x2 is equal to s2 is equal to s3 is equal to 0, x1 is equal to 2, x3 is equal to 8, s1 is equal to 24, s4 is equal to 5. So making that z is equal to 280. So considering whether this obtained equation is feasible to a normal existing level or not, or the obtained feasible solution upon performing these iterative methodologies will be obtaining this in an uh, has been obtained to a feasible categorization or not will be verified. And upon rearranging this and next performing the row operations with respect to R2 and eliminating R4, X3 in the given system, whether this has been identified or not will be verified. Next, each non-basic variable has a non-negative coefficient in row 0. Hence, 5x2, 10s2, 10s3 gives the current solution, and hence obtaining less than that is greater than or equal to 0. Hence, the current solution is specified as the solution exist within the concluding that these are having within the specified limitations that we have been discussed as far as our constraints has been given. So basic phenomena of this is the current solution declaring whether it is optimal in the range or not. So here it is, considering the row 0 is within the our conditional limitations, and consisting or concluding that the current solution is optimal, and the z value, the value that has been obtained, that is z value, z is equal to 280 for the company of the product furnitures, optimum weekly profit would be $280 if they produce 2 desks and 8 chairs. Considering 5 tables, excluding that is automatically having the demand for each and every week, but that constraint has been given to the only tables but not to the desks and chairs. Considering these unlimited categorizations for manufacturing, how much profit upon sales will be getting on the remaining two products, that is desks and chairs, will be specifying here, that is Dakota Furniture's optimum weekly profit would be $280 if they produce 2 dozen egg chairs. Right? We'll be having a glance once again how the steps of this simplex algorithm has been obtained, and the way of iterative process has been done indeed to get the feasible solution. We'll be having a look once again, converting the linear programming equation to a standard form, obtaining the basic feasible solution from the standard form, that is the standard form has been identified, and from that we will be identifying that the current value is feasible or not, determining that equation whether current basic feasible solution is optimal or not. If at all it is optimal, then we'll be stopping the program, or stopping the this simplification process. And if at all it is not having within the limitations or not in the BFS range, hence we'll be repeating the step 3 until and unless it is the current obtained values BFS is optimal. And how those will be getting done? By the concept of iterative process, it will be getting done until and unless the equation or new or at that particular time the current basic feasible solution is optimal, then we will be starting the equation, simplification. And here for that we need to consider these values standard form, identify these four different steps from the solution. First one, it is in standard form. All the constraints or equations and the variables are non-negative or not, should be non-negative. And any basic solution where all variables should be non-negative, and non-basic variables, in the chosen set of variables where variables should be equal to 0, and basic variable means the remaining variables that satisfy the system of equations at a standard form. So here standard form is nothing but all the constraints or the equations and the variables should be non-negative, or non-negative here it is clearly specifying. So that is the conditional strategy need to be maintained. And if at all it has been negative beyond the conditions of non-negative, it is negative when the RHS terminology to the LHS terminology shifting upon equating to 0 in the third step, the iterative process will be getting done. As in the example that we have been seen here, that the equations are being grasped here and solutions with simplex algorithm has been traced out here, and obtaining the standard basic, identifying the standard basic solutions, sorry, basic feasible solution, and determining to an current optimal basic feasible solution. And if at all the row satisfies with respect to the equating of 0, then we will be um, considering that equation or pivot equation as an basic feasible solution, and taking that value for the result categorization. And for that, the iterative process are involved, and hence the iterative process for the given problem that we have been done is, that is number of row operations upon eliminating the x1 category in 1 and next x3 category in 1, and by separating the slag variables, right? Row operations and the slag operations. Sorry, row operations are done for elimination of slag variables, and even entering of the uh, x3 or x2 variables, and identifying the optimal solution, and specifying that the answer declarations for the obtained value based upon the given question in the tabular format. This is the simplex algorithm methodology that has been applied on iterative process of solving in the case of this linear programming technology utilized for obtaining the basic feasible solution uh, in the complex range of problems in operational research technology. So here we'll be applying the uh, Simplex algorithm problem upon iterative process until and unless it attains the feasible solution. And this is a subtopic of linear programming, and we have been will be seeing in the next class that the dual concept mode or duality mode of solving the problem, which will be very much equal or very much easy for solving these linear programming problems applied in the different applications. Thank you.